In this video, we're going to take a second example of a related rates problem involving a triangle. This one involves the area of the triangle. Before we begin, let's talk about the steps that are useful in solving such problems. The very first thing we want to do is get a labeled diagram. Once we've done that, we will identify the known and unknown rates. Then, looking at the variables in those rates, we'll get an equation to relate those variables. Then comes the calculus part, where we differentiate with respect to time. Finally, using either algebra or arithmetic, we'll solve for any unknowns. In this problem, the base and height of a triangle are in flux. That means they're changing. The base is growing at a rate of 3 centimeters per minute, while the height is shrinking at a rate of 2.5 centimeters per minute. At what rate is the area changing at the moment when the base is 10 centimeters and the height is 15 centimeters? Is the area growing? We'll start with a generic triangle. I don't know that it's a right triangle, so I purposely make a triangle that's not a right triangle. And I identify side lengths, the base, and not a side, but the height. That is the perpendicular distance from a vertex to the opposite side. I note that the base is the growing quantity and the height is the shrinking quantity. And that'll mean that they'll have a positive and a negative rate of change depending on whether the quantity they measure is shrinking or growing. As I identify the known and wanted rates, I'm going to be careful to pay attention to the signs. Now, I was told that the base was growing at a rate of 3 centimeters per minute, so expressed in derivative terms, that's dB dt equals 3. Since the height is shrinking at a rate of 2.5 centimeters per minute, it has a negative rate of change, so dH dt is negative 2.5. Part of the question phrasing says, at what rate is the area changing? And that tells us that there's a wanted rate, the rate of change of the area, dA dt. I don't know what that's equal to. Now that I've identified the known and unknown rates, what I'm going to do is look at the variables in the tops of those rates and try to get an equation that relates just those variables. So the variables are the area of a triangle, the base and height of a triangle, and of course those are related by a very familiar formula. That is the formula for the area of a triangle, 1/2 base times height. In this step, I'm going to differentiate with respect to time, so now I'm going to do some calculus. Since I'm differentiating with respect to time, and time is not one of those variables, I need to be mindful that I'm going to be using the chain rule in these cases. So if I was taking the derivative of the area with respect to the area, it would be just 1, but I'm not. I'm taking the derivative of the area with respect to time. So getting rid of that diagram so I got more room to work, I'm going to call the derivative of the area with respect to time dA dt, which you'll note is the wanted rate. On the other side of the equal sign, I got a 1/2, that's a constant, times a function bh, which in turn is a product of two functions. So I'm going to treat this as a constant times a function and put down the 1/2, so there's the constant, times the derivative of the function will go in these braces here, and the derivative is going to be the derivative of a product. The product is between b and h, so I need the derivative of the first function times the second function plus the first function times the derivative of the second function. Hey, I just differentiated with respect to time. Now I'm going to solve for any unknowns. The way I'm going to do that is I'm going to replace the rates that I know and the lengths that I know with numbers that they ought to be. And the first one is, of course, dB dt, which I know to be that positive 3. dH dt, you'll recall we said was a negative 2.5, so just be mindful that you're replacing that with a negative number. And then the problem said that we wanted to know the rate of change on the area at the moment when the base was 10. So we can replace b with 10. And also at this time, the height was 15, so we replace the height with 15. Well, now it's just an arithmetic problem. So I do the arithmetic to solve for dA dt, and I get 10. 10 what? 10 square centimeters per minute, it turns out. And because that derivative is positive, we can say that the area is growing at this moment in time. Here's a follow-up question. Take a few moments to try this problem, following those same 5 steps. Pause the video, and the answer will appear in a few moments. So there's the answer. Turns out that the area was changing at a negative rate in this case. So the area is not growing, but rather it's decreasing at this moment in time. And we know that because the derivative is negative. Hey, thanks for watching.